Good afternoon, everyone. I'm Zhuangzi Xie, or you can call me Peter. I come from Tsinghua University, China. Thanks a lot for Professor Emilio, and it's my great honor to be invited here to give this presentation. I'm now doing some research and doing some experiment in Pisa University, and today my presentation is about the introduction of Tsinghua Thermodynamic Soil Model, or you can call it TDS, and parameter collaboration and laboratory tests. First, here's the contents. Research contents, basic introduction of Tsinghua Thermodynamic Soil Model (TDS), abacus subroutine of TDS, model parameter collaboration of TDS, and laboratory tests in PISA. The main aim of my master degree's research is to solve different geotechnical engineering problems by applying our constitutive model, which names TTS. For example, the suction casings used for the foundation of offshore wind turbines under complex loading and cyclic loading. We can use this TTS model to simulate it. My research work in Pisa now is aiming to study the movement of the leaning tower by applying TTS model. It is suitable to simulate the creep behavior happened in the subsoil of the tower. I had planned to perform a finite element analysis to predict the movement of the tower in the following time based on the test datum of Pisa clay, but this work haven't finished yet because of the limitation of the time. I just come here for 3 months, and I will keep working on this when I come back to China. So I will give a basic introduction of TTS. I know someone here is also doing some research on this constitutive model. Tsinghua Thermodynamic Soil Model, known as TTS, is a constitutive model which is set up by a thermomechanical method based on non-equilibrium thermodynamics theory and concepts. Yield function, flow rule, and other constraints of classical plasticity are not adopted in TTS, but plastic behavior of soil can be indicated by setting up the thermomechanical equations in macro level. I will give these equations later. And TDS can account for complicated soil behavior, including the nonlinear plasticity hardening, shear dilatancy, non-associated and non-coaxial, and rate dependence properties. TDS is originated from GSH theory. It's set up by Jiang and Liu in 2007. Cheng and Zhang, Cheng is my supervisor, Cheng Xiaohui, and Zhang is the first student, doctor student of Professor Cheng, improved it and made this theory, a theory applicable for geotechnical materials. Okay, now here comes to the equations of TTS. For the elastic part, a elastic potential energy function is defined here. Omega E is the elastic potential energy, and epsilon VE, epsilon SE is the volume part and the shear part of the elastic string. Three parameters are used, B, C, and C. If considering anisotropic behavior, then another parameter zeta is used to give the third part of the string, epsilon 3e. Actually, the stiffness coefficient is affected by density of the soil. So the parameter B is defined by B0 times exp B1 rho D. Two parameters are used here, B0 and B1, and rho D is the density. So we can see for the elastic part, actually four parameters are used. That's B0, B1, C, zeta. Sorry, five parameters and C, right? And stress tensor equals to the derivation of elastic potential energy by strain. So we can get the normal stress P, shear stress sigma S, and the stress which shows which shown the anisotropic part of stress sigma 3 here. For the plastic part, a two entropy theory is put forward. It equals to real entropy plus the granular entropy, and our equation is given here. Sg is the granular entropy of unit mass. Rg is calorific value of granular level. Tg is granular temperature. I in this equation is the volume convert from granular entropy to real entropy, which can be assumed as a linear function of Tg. So I equals to gamma times Tg. Sg and Rg can be indicated by function of Tg and the rate of strain separately. So then granular entropy function can be transformed into the following form. In this equation, M1 to M3 are migration coefficients. Last, the change in granular temperature Tg leads to inelastic deformation, which can be indicated by the elastic relaxation equation. dt epsilon ij equals to dt epsilon ij for the elastic part plus yij. Yij here is the relaxation rate, which is decided by present elastic strain and granular temperature Tg. The equation is deformed into the following form. Here, A decides the rate dependency property. So basic equations of TTS constitutive model are given below. The first equation is for the granular entropy equation. The second one and the third one gives the bridge between the granular entropy transformed to the real entropy. And the last two equations is for the elastic part. Then when we get the strain rate for shear and volume, you can see in the first equation, then we can get Tg. And by using the second and third one, we can get the change of epsilon v in and epsilon d, actually epsilon s for the shear strain in elastic part, and we get these two into the last two equations, then we get P and Q. 10 parameters are used in TTS, that's B0, B1, C, C zeta, and 4 migration parameters, M1, 2, and 4, and A affects the rate dependency. Now we have already get a ViewMax subroutine of TTS in Abacus. It is coded by another student by Professor Cheng. An increment form of effective stress relative to time is adopted. Granular entropy function and elastic relaxation function are two ordinary differential equations. and using a fourth order range quota method to improve the numerical accuracy. We use this subroutine to simulate a triaxial shear test with constant rate of strain. You can see the results here. Uh, in the in this corner, you can see we use this abacus program and also use it in a MATLAB program. We got the almost the same curve. I've done a simulation of 1D creep here, actually in Pisa, and you can see the curve skips here, the stress, TG, and strain with time. Let's put our eyes on the TG. You can see when I put the force on the top of the soil, the TG comes to the peak first, then it goes down slowly. That's the relaxation process. Uh, the granular entropy is goes to the real entropy, so the strain keeps increasing in the whole time. For the parameter calibration, TDS is quite strong but complicated. Most model parameters are difficult to be calibrated. There are three different methods I put forward. An analytical solution given by Chen Zhihui is a former student of Professor Chen, come up directly from the equations. In order to calibrate the parameters without solving ordinary differential equations, results of some uncommon or strange tests are needed. Isotropic consolidation triaxial compression and rebound test at two different confining pressure, and undrained shear test reaching critical state line, and then stress relaxation. These two tests are used. Here are the equations of Chen's method. First, he used an triaxial compression test to get the parameter B and C, and then use the shear to critical state to get C and zeta. And last, he used a relaxation test to get the migration parameters M1, M3, and M4. Let's talk about the disadvantages of Chen's method. First, lack of data of these two tests requested, because they are too strange and uncommon. And the equations are patched together without physical background. For example, you can see the Q square in critical state divided by P square P at critical state. We all know that Q divided by P, that's M for physical meaning, but in this way, Q squared divided by P is only a mathematical equation without any physical background. And the propagation of arrow is serious. For the former uh, page of PPT, you see first he get B and C, and he used B and C to calculate C and zeta. Then he used B, C, C, and zeta to calculate M1 to M4. So the arrow is propagated for each step. Last, the equations are yield conditioned, very sensitive to the initial value. So most of these disadvantages are found for the first time because no data for these two kinds of tests can be used before, but I did them in PISA with the help of Professor Squiglia I will talk about this test later. Zimnis of MIT has given another collaboration method by control varieties method. She pointed out the influence of most parameters by changing them one by one and keeping the others constant. For example, she indicated that B0, this parameter, uh, affected the position of VCL, the virgin compression line, and B1, this parameter, affected the slope of VCL. She gives a good way to analyze the effect of each parameter. However, some of the explanations seems not so reliable and feasible to use. For example, for the M2, this parameter, she said that M2 affect the uh, intersection point between the VCL and the reload line. But you can see it's hard to tell uh, from m2 equals to 50 to 300, that 6 times, but the curve doesn't change so much, so we can hardly use this method to collaborate m2 because the test data is not so beautiful, so it's hard to tell which m2 is better than the other one. An analytical solution is not given for her method, so the collaboration process needs to be very empirical. I'm trying to carry out a new method by combining the common test types with analytical solution. Only the results of engine shear test, isotropic consolidation test, 1D compression test and 1D creep test will be needed. Most parameters can be decoupled, and this work haven't finished yet. I will keep working on it. Here's some equations for my method. For the last part, I want to make some discuss on the laboratory test. I did them in Pisa with the help of Professor Squiglia. Actually, this is the first time I do some test, and also Professor Cheng seldom do laboratory test. He's working on the theory part, so we cannot give a good explanation for the test curves. So you are the experts on this part, so I need your advice. Uh, the test is about engine shear test reaching critical state line and then relaxation. It is a test which is needed by, uh, I have mentioned previously, the Chen Zhihui's method for calibration. I did them for the first time. Here's the consolidation curve for cell number 1, 2, 3, 4. I did 4 tests now. Actually 6 in total, but only 4 tests are finished yet. And here's the engine shear and relaxation curve in P and Q, this axis. And the last is the relaxation of log T with Q curve. Okay, maybe we can discuss this later. And I have finished my presentation. Thank you for your listening.